Again, I would like to thank again for inviting us to share some of the research that currently I'm doing on renewable energy and also smart grid and the microgrid area. So the title of my talk today is that challenges and opportunities of integrating large-scale electric vehicles in smart grid with renewable generation. So that would be my overview of my presentation. So initially, I will start with some background and motivation. Then I'm going to show some of the work that I'm doing on electric vehicle car charging system and also electric vehicle modeling and also integrating large-scale electric vehicle in the smart grid or microgrid. And then I'm going to briefly show some of the other projects that I'm currently leading at UTS. Now, as you know that due to this large-scale renewable energy integration or energy transition, there are several changes happening in the power grid. For example, if you think about the generation side of the power grid, in the generation side, mainly the large-scale centralized fossil fuel power station is being replaced by small size renewable generation. Because as you know that currently most of the power is coming from centralized power station, which is mainly powered by coal, gas, and other fossil fuel source. Now, if you go to the transmission sector, due to large-scale renewable energy generation, there are some changes happening. For example, you will see many fast, like accurate measurement and monitoring devices. For example, phasor measurement unit, many power electronic-based controller, for example, STATCOM, SVC, and also high voltage DC is getting more popular than high voltage AC. Now, the biggest changes actually happening in the distribution sector, where you'll find many small size distributed generation, for example, photovoltaic system, wind turbine, biomass, and so on. So another technology also getting popular, which is microgrid. And then you'll also find many smart meter, and then new types of load, which is plug-in electric vehicles or electric vehicles, which is actually the main topics of my presentation. Although, I mean, I have done work in all of this area, but today I'm just going to highlight on electric vehicle side. Now, even after the electricity meter, many things are happening. For example, building energy management system, zero energy homes, and then energy pricing and so on. Now, let's move on to the electric vehicles. Now, the electric vehicles is actually not a new technology, also is getting popular now. But the first electric vehicle that was actually built in 1981 by a chemist from UK, whose name was William Morrison. So the first vehicle was built in California, USA. And the maximum speed of that vehicle was 20 miles per hour. That vehicle was powered by a 24-volt battery. And with single charge of the battery, the vehicle could run maximum 50 miles. Now, after that, almost like more than a century, there was nothing much happen for electric vehicle due to political and other reason. But as you know that in recent year, the electric vehicle is getting popular all over the world, including Australia and other countries. And the reason behind this, because the transportation sector actually is responsible to produce almost like 1/3 of total greenhouse gas emission. Now, as you know that most countries, they have set a target to go net zero by 2050. Now, to achieve the target, I mean, the transportation sector has to be electrified. And that's the reason that by 2050, most of that currently IC engine-based electric vehicle actually will be replaced by electric vehicles. Now, there are actually a number of reasons, I mean, why that electric vehicle is getting popular. And the first reason is that is lower lifetime cost. Although you can say that the upfront cost for electric vehicle is very high, like when you buy, the price is still high. But if you compare the lifetime cost, actually today electric vehicle is less expensive than the normal IC engine based vehicle. And here you can see that initially the electric vehicle was costly than IC engine based vehicle, but after a few years the electric vehicle is cheaper than the IC engine based vehicle. And there are a number of reasons. Because it's cheaper to charge, then you fill the tank with the petrol. The electricity price is much more stable than petrol, because petrol price actually varies even like in a week time. For electric vehicle, it has got less maintenance cost, and many countries they are providing like there is no toll, and also many government also providing subsidy or giving tax free when you buy to a new electric vehicles. And with one set of battery, you could almost run like the 50,000 miles with a single battery. And if you, with that lifetime cost is already cheaper. The second reason for getting popular, that the efficiency of the IC engine based vehicle is very lower. Now this figure is just showing some data from 2025 Toyota, but even if you use the recent vehicle, the efficiency would be in the range of 20%. Now what you can see here, for example, if you have a Toyota 2005 vehicle, you are taking, for example, let's say 100-liter petrol. Out of 100-liter petrol, what is happening? Almost 76% energy is lost in the IC engine. And on top of that, another 8% energy is lost like idling. Idling means that your vehicle engine is on, but you're just waiting in front of a red signal or traffic jam. So at the end, only 16% energy is transferred to the drive line. And in the drive line, another 3% energy is lost as like a mechanical loss. So at the end, you are getting only 13 to 20% efficiency. But for electric vehicle, the efficiency is much higher. So if you compare the overall efficiency, considering the losses in the inverter, charger, motors, and all of them, efficiency is more than 80%. So it is much more efficient than IC engine based vehicle. And as I said, it's lower maintenance, because for electric vehicle, there are no spark plug, there are no timing bells, there is no oil change. And as I said, like the electricity price is lower than the petrol price. And here I just compared the running cost per kilometer for different types of vehicle. And the battery pure electric vehicle is, maintenance cost is lowest compared to either plug-in or hybrid or even IC engine-based vehicle. Now, even if you compare the running cost of electric vehicle much cheaper than the IC engine-based vehicle. Here we just calculate the price per kilometer with Sydney electricity price. And here you can see that EV, hybrid, and IC engine-based vehicle. And you can see that on the price per kilometer. So for EV, it's 20 times less than IC engine-based vehicle. And also, as I said, like it is environment friendly. The emission is much lower than the normal IC engine vehicle. Now, in terms of technology, there are many technology available which is powered either by battery or hydrogen fuel cell. And even for battery, as I said, like it could be a hybrid electric vehicle, plug-in hybrid vehicle, or pure electric vehicle. But I think in coming years, the pure battery vehicle would be most popular for small scale car. But for heavy vehicle like truck, train, maybe fuel cell powered electric vehicle would be more popular, because for heavy vehicle, probably you need like frequent charging. In that case, hydrogen would be better choice than the normal electric battery. Now, if you want to buy electric vehicle, there are a few things you need to consider. For example, let's say what sort of driving range you need for your daily uses. what sort of charging infrastructure you have. Is it like charger level 1, 2, 3, and 4, which I'm gonna discuss next slide. To consider if you're planning to buy a electric vehicle. Now, there are some challenges why the electric vehicle number is still not very high. And here I have mentioned some of them. And I already mentioned like the cost of electric vehicle, range of electric vehicle, and also the charging infrastructure. But the good news is that the battery price is going down almost like 15% every year. The range of electric vehicle, although the average range is like 135, 140 kilometer with single charge, but the latest Tesla, you can actually run 700, 800 kilometer even with like a single charge. But the country like Australia, sometimes if you want to visit from one state to another state, for example, Sydney to Melbourne, maybe you need to charge it in the highway. And good news is that the charging infrastructure also now is getting quite common in the highway as well. And as I said, like these are the 4 different charging standard available based on the power and so the time you need to charge the battery. And definitely the DC fast charge, you need only 10 to 15 minutes to fully charge the battery. And also the new technology is also coming, wireless power transfer. And if that technology is getting matured, then while you are just driving your car, within a second, your battery will be fully charged during the induction principle. Now, we collected some data in Sydney just to find out on an average how many kilometers people run per day. And here we found that more than 88% people, they just drive their car less than 30 kilometers per day. And as I said, like with 135 kilometer range, even it would be more than enough for those like daily uses. But as I say, like that in the latest one has got very high range as well. So the range is not a problem anymore. So that's more like the electric car, but also for electric bus, the similar charging technology use. So again, it could be either plug-in or wireless. For plug-in, there are 2 types. One is called like plug-in and another is like the pantograph. So the plug-in one, same like the electric car, you will plug the bus with the charging system that will charge. But the most popular one is called the pantograph one. So the pantograph one, that when the bus is just stopping, either to take more passenger, and during that time, there would be like an overhead charger, which is automatically connect with the bus's charging system. And then the bus will actually get opportunity to frequently charge. And that's how, it will not need a very bigger capacity. But if you use just standard cable, because the bus will run the whole day, you actually need a very high battery capacity, which is not economical. Now in coming years, you will having that electric car charging system like in the industry, in your office, in your home, in the shopping center, and so on. And as I say, although that electric vehicle number is quite low, but as I said, the number is actually increasing significantly. But in some of that European countries, they already have like more than 40% vehicle are like electric vehicle. For example, one of the example is Norway. But in Australia, all the number is quite low. But by 2030 or 35, almost like 30 to 40% vehicle actually will be electric vehicle. Now, what happened? Like when you have got significant portion of the vehicle or electric vehicle, the electricity demand on the grid actually will go up significantly. And if we can't actually take appropriate action to actually control that charging and also discharging of that battery, it will have significant impact on the electric vehicle, on the power grid. And here the top 2 figure, you can see that on the black one, the current electricity demand in 2 of the states in Texas and California. And if they have got 100% electric vehicle, so the blue one would be that additional demand on the electricity grid. And the bottom figure that actually shows that additional power requirement from the electricity grid. When they have got like 100% vehicle will be that electric vehicle. So what I'm trying to say that it will have significant impact on the power grid in all countries, including like Australia, Indonesia. So we actually need to have a proper plan how we're going to manage that large scale electric vehicle in the power grid. Now, when you have got large scale electric vehicle in the power grid, there will be have a number of challenges. For example, it will have significant impact on the power quality, voltages, frequency, and so on. But the good news is that the latest technology, which is called vehicle to grid. So it's not only that you will charge the vehicle from the grid, but it will also have the capacity to feed power to the electricity grid using this technology. And once we have that technology, actually it will be able to solve some of the problem that has been actually introduced by large scale renewable power integration. But although, this technology has got potential, but still there are some challenges that we need to address. For example, as I said, this one could be the source or sink of power. It has got very high reaction time. This is like an intermediate mobile source because, you don't know the exact location of the electricity vehicle. So if you can actually address those challenges, it can actually have positive impact instead to have the negative impact on the power grid. And this technology, vehicle to grid, is already actually available in the market. And there was a project happened in Australia, in Canberra. In this project, during the COVID time, what happened? This guy, he was just participating in this trial. While during the COVID time, he was not driving the car. What he was doing, he was just buying that electricity pipe during the off-peak time and selling back during the peak time. And that's how actually he make actually quite good money while his car was just parked in his driveway. Now, next, I'm going to show you some of the results that I have got from some of my project. For example, in one of the projects, we actually design a quite a smart onboard car charging system. Here we used quite latest switching technology, silicon carbide MOSFET, which has got very high frequency. And also we use very high frequency transformer, which has got very higher efficiency. And for this transformer, we managed to get more than 98% efficiency. But the good news, contribution was from our side that we included number of new control capability with the car charging system, which not only charge or discharge, but when it is connected with the home or grid, it can actually solve many of the problem that has been actually created due to large scale renewable energy integration. And some of that control function here, you can see that it can charge, discharge, it can provide ancillary service like reactive power control, voltage control, and also harmonic power, harmonic reduction. This is the circuit, but I'm not going to discuss because that's already published. And if you are interested, you can download and read it. We actually use the standard topology, but as I say, our contribution was to design all this control, which is implemented through PWM technology in the inverter. So that's like summary of all the control. I'll just skip that one. And then we actually did number of tests just to show that, it actually can be, really it can provide those functions that I mentioned. So here you can see that this is connected with a house. This is just showing that it charges. So the charging is started here. So before that, there was no charging current, but here you can see that it's charging the battery from that grid. So the next one, it was also showing that it not only charging, but it can actually provide leading reactive power to the home, actually to control the power factor and also the voltage as well. And here you can see that there is a angle difference between voltage and current, and this angle is leading. So that means it's actually providing leading power support to the system. Because what happened in most of the cases, most of our load in our home are lagging, which actually sometimes cause lower power factor, and that cause power quality problem. And also it has got high electricity bill as well, because the losses actually become higher. So once this is connected, it not only charging, but it also solve that lower power quality and power quality problem. And this one just showing that it can actually improve that power quality. So here you can see that the source current is quite distorted, is not a sine wave. But here, this is before connecting our charger. But after connecting the charger, you can see this source current is quite smooth and sinusoidal. And in terms of percentage, before connecting our charge to that particular home, the total harmonic distortion was 25%. But after connecting it, actually gone back to 3.2%. And the standard is that it has to be less than 5%. Not only that, this charger also has got another capability, that it can actually transfer power from one vehicle to another vehicle. For example, let's say that, you are driving in a remote area where there is no car charging system available, and suddenly your battery gone empty. So the current practice is that we call like insurance company, and that insurance company come with a big truck with the battery, and then it charge your battery, and then you can again run your car. But the good thing is that if someone use this car charging system, if you have got two vehicles nearby, it can easily transfer power from one vehicle to another vehicle. And also we compare the performance of this one with a US patent in terms of the overall efficiency and also the capability as well. And this one has got the safety feature as well, that when it is connected with another vehicle, you can't run unless it's disconnected. And that control function is provided with this control pilot and proximity port of that particular V2V cable. Now this one shows again that one of the vehicle is charging and another is discharging, just to prove that concept that I mentioned earlier. Now this is more like the technology level. Now what happened when you have got 100,000 of vehicle? The first problem that we try to find out how actually you can actually estimate the demand that you need from electricity grid when you have got so many electric vehicle. And there are actually a number of uncertainty if you're gonna model that electric vehicle demand, because you don't know how many kilometers you will be running per day. You also don't know what the your starting location, your destination, the road condition, traffic signal, the driver behavior, what sort of car charging technology you are using. So there are so many uncertainty are involved. So here, in one of the projects that I was involved, just to design a car charging system for a shopping center. So there is a shopping center nearby our university. So we collected some data from that particular shopping center, and then we designed that the conceptual framework. And here you can see that there are AC bus, and then some control switch, then some inverter, converter, and there is one mobile battery and some electric car charging system with some control switches. And also in that shopping center, there's a photovoltaic system as well. Now with all of this technology, we actually developed that mathematical model with all of that uncertainty that I mentioned previously. And here, again, I documented all that uncertainty that I mentioned here. And then using some mathematics, and again, I'm not going to discuss all this mathematics, but solving those mathematics, we managed to get some probability function that actually give us arrival time, departure time, like what time the vehicle is coming, what time is departing, and on an average, I know what sort of power is needed for a particular vehicle. And then considering all different type of technology, we managed to get what would be that particular demand for that particular shopping center, and then what sort of power we can get from that photovoltaic system. We use that real temperature and the radiation level that is available for that particular shopping center. And then using all those multi-color simulation and stochastic modeling, we managed to develop a optimization algorithm that actually give that what sort of capacity need for that battery, and then what sort of capacity need for energy need, so that it actually does not violate the maximum capacity of this cable, of the transformer and everything. And then we compare that what will happen without optimization, and if you just design the system considering all that factor that I mentioned. And what happened, like if we don't consider all those optimization factors that we have considered, we did simulation and we so that sometime it actually violate the capacity of the transformer, which is not actually accepted by the power grid. And also we did cost benefit analysis with different sort of the battery capacity and so on. Now I'll just show you one more application with the technology that we developed, and then I'll just try to finish it. So the next application that we consider 3 different technology, like the photovoltaic system, normal battery and electric vehicle, just to show that if we have got a city, for example, let's say like the Jakarta, and here like I consider Sydney. Like if we use that 3 technology, and then if we actually control that charging and discharging of all this battery, how actually we can reduce that overall peak demand of that particular city, which actually will contribute to make the system like more energy efficient, and at the same time it will also reduce the electricity price. Now here to do that, actually again, I mean, we consider different sort of control. We also consider the remaining capacity of the battery so that it doesn't interfere with the daily uses of the electric vehicle. Now with all of this, we developed that model. And then we implemented both in the software platform and also in the laboratory with the smaller capacity. And here also we developed some optimization using the decision tree and also the artificial intelligence. And then we also compared on the performance with both this technology. And then we collected the real data from one of that electricity distribution utility, Osgrid here. And then we implemented our algorithm with the current electricity demand. So you see that the red one is the current maximum demand. But if we use that algorithm that we mentioned here with 2 sort of electric vehicle, one is like a small size battery capacity and another is like large battery capacity with blue and green, you can see the electricity peak demand can be reduced significantly using that algorithm that we mentioned. And again, we compare with the artificial intelligence based algorithm as well, just to validate our idea. And then we implement it in the lab as well. And just to show that actually it can be actually implemented for a real system as well, using that real devices in our laboratory. Then currently also I'm doing some of the project in the microgrid, and one of the project funded by Australian government, which is almost like $1.6 million. And we are actually building the real microgrid. And also here we are developing different software and control algorithm for like the real-time monitoring and also the control forecasting everything. And also we are connecting with the particular community in that particular area just to like address what sort of concern they have in that particular microgrid, which is like running in the 2nd year. And if I get another opportunity, maybe later, I can show some of that technology and algorithm we are developing from that real microgrid project that I'm doing. And here we have got a number of industry partner involved from like the technology level, also the power grid. And here also you can see some of that microgrid that even we have our on campus in the building as well, with different sort of battery, inverter, converter, and monitoring and control devices. This is another project also funded by Australian Research Council on the microgrid. And here we're actually developing some smart energy management system with like a small scale building and commercial type microgrid. And also in our lab, we actually have got all that infrastructure that need actually to do actually real-time experiment with photovoltaic system, wind turbine, different sort of inverter, converter, and also that OPLRT technology, which has got fast computing power and also the control objective as well. We have also some interest in the cybersecurity side of the smart grid with large scale renewable, because that this is a quite significant issue for different countries. And fortunately, actually, I actually was involved in one of the projects that funded by New South Wales government. So that's all I would like to share. I mean, due to that time restriction, I can go details for all of the research that I'm doing, but these are some of that current research interest in my group. So I have got a number of PhD as well as postdoc. They are working in this area. So thanks for your attention. So during the Q&A time, I mean, I'll be more than happy to talk to you further if you have got any question or comment. Thanks for your attention.
Thank you very much, Arko, and thank you, Dylan, and thank you everyone for attending this guest lecture. My name is Quang Ha. I'm supposed to do this guest lecture on multi-scale air quality monitoring for smart city. Let me enlarge the screen. Okay, so yeah, apart from this, my research in automation and control, recently I use AI, and we worked with the Department of Infrastructure and Environment, DPA planning for this project targeting smart city. So an outline could be about smart cities, air quality, air pollution modeling and monitoring, and global scale, local scale monitoring, and wide multi-scale, and air quality monitoring for smart city, and a conclusion. I would like to mention that I think this lecture is for students. So basically, I don't go too much in depth in research, and more or less it is more kind of information for inspiration. Now, I would also like that this lecture would be interactive, so you can interrupt me anytime, and maybe time in your chat box any question for me to answer. Well, so I would like to ask, what is the population of Indonesia right now? You can just say interact with me. Hello. I guess there is about the 200 million or more, right?
280 million.
273 million.
Yeah, exactly.
Okay. So, and can I ask which country is the most populated right now?
China, India.
You're right. China was in the past, but from April this year, India become now the most populated country in the world, over 1.4 billion. So you can see that the need for urbanization is there. After a while, then you see that the population in the cities is outnumber the population in the rural. That was dated back in, I think, before 2010, and nowadays this gap become bigger and bigger. What it means is the people tend to live in the cities, okay? And then, so the world population is expected to increase 68% by the year of 2050, with 2.5 billion more urban residents. And then what we need is a sustainable solution. Of course, we can't have more land. We have a limited the land size, but the solution out there are biotechnologies, and that's why we think of making biotechnology to make our city smarter. So can I ask also which country is the most advanced in science and technology nowadays? Of course, I think you don't answer, but United States. Okay. And which city is the most typical for that country in terms of high tech? I think, or other words, which city you think is the smartest? So here is the New York City. Yeah. So I can bring with that video. I think to be short, their population is nearly 9 million. And you see that apart from all others, the most important is the data. So I think you can search the website, but I like to move on to say what are the characteristics of a smart city. I can show you this diagram where you have a society, which is the people. So smart people and the quality of life. So smart living and environment. So smart environment. And what next? Smart governance. So you have a government that can use open data, infrastructure, admin, and provide online service to all the citizens. And then you need also a good economy. So smart economy, enterprise, innovation, culture, productivity, local and global connections, and also smart mobility. We live, but also we need to travel. So infrastructure should be good, efficient transport, affordable transport, and multimodal mobility. So you can have a variety of transport means to use. So in short, what is a smart city? A smart city is a municipality that uses information and communication technologies to achieve what? To increase operational efficiency, to share information with the public, and to improve both the quality of government services and citizen welfare. Okay, so you can see that with advanced technologies, we can reach a city to make it become smarter via, for example, Internet of Things, intelligent shopping, smart health, good education, smart buildings, smart home. On road, you can see that electrical vehicles, like Professor Hossain mentioned, and we have a smart grid, smart energy to sustain. So with that, what are the key technologies for a smart city? You can see that we have, in general, 5 technologies. First is smart energy. We need enough energy. That includes, for example, electric car, smart grid, like Professor Hossain mentioned, or smart transportation, where EV is on the road and it is connected to the grid, for example, and smart data, where you can communicate and you can retrieve all the data necessary for your life, and also smart IoT, Internet of Things enabled devices. So everything hooked up to the network, and you can identify anything on spot. So also smart infrastructure, because we need transport, as I mentioned. So what is that? The smart city should be interconnected, should be interactive, and should be interbeing. So which among the 6 factors that make a smart city? Smart people, smart living, smart environment, smart governance, economy, and mobility. What is the most important? Of course, we are humans, we live, probably I think the most is coming from life. So in order to live a healthy life, enjoy life, then the 2 essential factors is number 1, water, and number 2, air. And that's why every day we breathe, every second in life we breathe. And do we breathe the right air quality for our healthy body? Okay, so what is air quality? I should mention that according to the World Health Organization, 99% of the global population breathes air pollutants that exceed the limits. Okay, so air pollution as there, it is a problem. It is a contamination of the indoor and also outdoor environment by chemicals, physical or biological agents, and household combustion devices, motor vehicles, industrial facilities, forest fires, and also other sources are common to contribute to the problem, serious problem of air pollution. Pollutants of major public health concern include what? Particulate matters, dust, carbon dioxide, carbon monoxide, ozone, nitrogen oxide, sulfur dioxide. Outdoor and indoor air pollution also cause respiratory problems, okay? And it can cause morbidity and mortality. You can die. In fact, the fact is that the combined effects of indoor and outdoor air pollutants can cause 6.8 million premature deaths per year annually. Okay, so I want to mention air pollution is a silent killer. Yeah, even in Australia, you can see that we, although enjoy healthy air, we also have some days that exceed the normal standard. And the question also, are we safe from low level of air pollution? The answer is just be cautious, because even lower concentration of air pollution, it can cause a serious problem accumulated. So reducing the level of air pollutants will also contribute to slowing climate change. And that is the fact from scientific research. In fact, Harvard research says that even low level of air pollutants can cause a problem for health. So what is air quality? We mentioned air quality in a quantification. So we need a level, and that level is air quality index. So we monitor air quality as we try to identify that air quality index compared to a threshold, okay? So that we can have a good or clean air, or medium, moderate, or unhealthy, or a little bit for sensitive people, or unhealthy and very unhealthy or hazardous. So this kind of gases like CO, CO2, or formaldehyde, or nitrogen dioxide, etc. Ozone, background ozone is a harmful gas. We know that ozone over there is protecting the Earth from radiation, but however, at the ground level, it is a air pollutant. And also dust is a serious problem, and also volatile organic compounds, etc. So what is the air quality index calculated? Normally it has a number, right? A number. For example, I use this index number for these gases: CO, CO2, hydrogen, ammonia, ethanol, hydrogen sulfide, toluene, or there. And apart from that, oxygen is a good. We need that. So you see that this air quality index for air pollutants, when it is low, it is good. But when it is higher, then it's coming to unhealthy, unhealthy likely, or unhealthy, very unhealthy, and hazardous. where oxygen is reversed. We need it. So the lower the problem for us. Okay, and in order to have that number, we need kind of a threshold. So it has a breakdown, breakpoints, and breakpoint is determined by expert. So medical professionals together with scientists work out for that breakpoints, and we compare with that breakpoints in order to calculate for the index, and that index is given in a table. It looks like that. So with that, when I prepare this lecture, I check, for example, AQI in Australia. You can key in, and then you can find this from the website as I did here. So you see that it is rather good. Just very moderate. Okay, but if I check with Indonesia, I think in general it is moderate, but some city is kind of unlikely in a serious concern somehow. Okay, so it is likely above the threshold, and some might be unhealthy. This university, I think I checked, it is also above the concerning threshold. So how we can have that AQI, we need to use this kind of air quality models, and a model for that is mathematical simulation of how air pollutants disperse and react in the atmosphere to affect the air around. Okay, and there are three components to be considered. Number one is species emission. Number two, transport. Number three, physical chemical transformation. This is where all the reactions, for example, photochemical reactions from ozone or other chemical reaction participate in here. And that components will besides the removal process and meteorology. Okay, so in Australia, normally the CSIRO scientific organization here propose the use of TAPM CTM, the air pollution model, chemical transport model. And now later on they developed, which is currently used, is CCAM CTM, cubic conformal atmospheric model, chemical transport model, where you see that emissions inventory is here. Inventory is a collection of data where people measure at a certain time and record on the data, and then emission models, and then we have meteorological information data coming here, and first the modeling, and then the chemical transport model go, and finally it gives you the concentration. In the US, they use CMAQ, which is the community multi-scale air quality CMAQ here. You can see the block diagram from there. That is some. Of course, there are some countries that also have other models. And what are the modeling methods? You can see that air quality is a profile that are spatially distributed. Okay, it is throughout the city, or throughout from city, from the state, and from the state nationally, and linking between country and country as well. So it is a spatial distribution, and it is also a time series, because it is a collection of data from right now, from the last 3 days, last week, last month, and also for the years, and not only the years in the past, but also the problem for us is that we want to know exactly the forecast of air pollutants in the next 3 days. Normally, we give 72 hours for that. So we have a spatial temporal profiles. And for that, there is a problem of probability and statistics go in there. So we need to know some statistical characteristic like the mean, the average, the median, and also expectation, etc. And data analytics are a tool for you to analyze on that. So they are numerical methods. And for example, ARIMA, autoregressive integrated moving average model, which is popular to analyze and to represent the stationary as well as the non-stationary time series are used in India. Now, these models are also photochemical tools, as I mentioned, because it contains also the embedded photochemical reactions there and disperse tools, and also inventories where the people, the authority need to record by measurements to give you the initial data for the calculation, for the modeling. And it is deterministic via probabilities, because with the model, you can use some deterministic tool, but also it involves the probability. And satellite data also using for remote sensing and imagery. So right here in Australia, we have this meteor satellite launched, and you can see that the bushfire we have 3 years from now, from the summer 2020, can be captured by satellite instantaneously, basically. So we can have that smoke plumes visualized here. Now we have also sensor networks and low-cost wireless sensor networks. Sensors are there available for us to use. I have here one chat box finished by 2:10. Okay. Okay, I will try to finish by 2:10. And then we have AI, machine learning, and deep learning neural networks for us. And it is a problem of global scale and also local scale, where we can have the microclimate, and for example, in this house, in this building. And it is a problem of big data where ensemble model. Okay, my project working for DPE is how to develop the ensemble model in order to improve the accuracy of the air pollution forecast for New South Wales. So to do that, normally the DPA, it has kind of 5 regions: the Sydney City and Upper Hunter, Lower Hunter, Illawarra, and rural, and under a organization to accredit it. Okay, and here is the image of a station, monitoring station, where we can have observation like a benchmark for us to work out on the data. But right here, you can see that is a sensor network. Sensor network here coming from purple airs. You see that it is mounted, it is co-located to collect the data. Where you can see all the data that collected from the sensor. One problem is that for the sensor, it has to be reliable, and it has to be dependable in a sense that it can be available, it can be reliable, it can be fail-safe to guarantee the accuracy and the availability of own data at own time. So that together, it is an ensemble model. You can see that observation come in here, where also data come in here from low-cost sensor network, and here from meteor data, and this kind of thing where the learning mechanism here is developed in order to handle all the uncertainties and to improve the accuracy of the forecast. Here is somehow image capturing the idea of low-cost sensing network using Purple Air. And we developed for that prototype of the website where people can access that incorporated the deep learning the neural network here, and also the low-cost sensing network data. So inside the buildings, we have that Wasmos connected to IoT. And for example, in our building in here, and then we can have the monitoring data at on time for the students and staff inside the building. You can see that one student in the lab, she did have a problem, and then we prove that, okay, the air quality index is okay, but what it is also humidity involved in that, and it may be an extended indoor air quality index that better reflecting the situation with health of that student and in general. Okay. So here is the calculation where we use extended fractional Kalman filter with Matek function covariance. I don't go to in depth in that. And then we have the concept of a smart building where renewable energy are there on the rooftop when this building that I'm working in receive a governmental $50 million from the government to build a smart grid on top to prove that the penetration of renewable energy sources, and also demonstrate that the building management system, energy management system, and also sensors are embedded in the structure and can be used for monitoring indoor air quality, as I mentioned. Okay, here is the diagram for that. Now, for the suburb, we recently working with a suburb in order to monitor the air quality to make the suburb become smart, livable neighborhood. Okay, so we extend that work for another suburb, Melrose Park, where on the development, the industry won a big project to build this into this park into a livable municipal area. Okay, and I would say a lot of sensor. Yeah, you can see that the project is installed there. Okay, probably we don't have a time much, so I should move on to meet the time. But I want to mention that it's a finer scale of monitoring and prediction, where when we develop in a city some construction site like that, then we need to also guarantee the air quality so that air pollution do not exceed the limit, right? So dust or particulate matter need to be monitored so that the emissions are in the range allowable. And you can see that the park become on the building side on there is monitored via a low-cost sensing network with sensor modes. So the development in Sydney are still moving on. Currently, we have, I think, around 26 million, but expected to increase in higher. So yeah. So currently the population is there, but expected to reach 30 million. And together with that, the Sydney population also increase. And then the New South Wales government is going to build, is already built on the way of build a new airport. This to be commissioned and put into usage in 2026. So in conclusion, I want to conclude to meet the time that we need to stop here to say that air pollutants are harmful to human health and need to be monitored. Air quality models and many information sources are used for monitoring purposes. Also, developing urban areas in smart cities has to include solutions for air quality monitoring to reach sustainability and resilience. Smart technologies are available for monitoring outdoor and indoor air quality at global scale and local scale. Okay, so I think I try to abide by the time constraint. Yeah, thank you.